Now, as we consider the surface of the Earth, one of the things that has been discovered is that there are these crustal plates that make up the surface of the Earth. You can see, for example, this line here. It's you can trace it around. You can trace around, and you can kind of see that there's a plate there. Here's a little bitty plate right here. And these plates are basically floating over the mantle and they're able to move independently. Now, if you look at the edge of South America here, you can kind of see that it would sort of fit if you were to move it to towards the coastline of Africa. If you move it and tilt it a little bit, this part here would just kind of fit right in there. And people noticed this quite a while ago, and it gave rise to an idea called continental drift. And we now know that these crustal plates are actually moving relative to one another, causing the continents to drift further apart and closer together over very, very long periods of time. Now, at plate boundaries, that's where one plate comes together with another. As these plates push and rub against one another, that can create earthquakes. It can also cause volcanic eruptions to occur. Basically, these plates coming together can cause tremendous amounts of pressure, and as the pressure is released, it results in these kinds of geological activities. And as you know, earthquakes and volcanic eruptions can be very, very destructive. Now, when you're looking at the Earth's upper mantle and you're near a plate boundary, something that can happen is called a subduction zone. And that's basically where one plate collides with another and then pushes in a way that it slides underneath it. So when this happens, part of the Earth's crust can actually be driven down into the mantle. And this is a geological process that takes place over many, many years. Now, the opposite process can occur when two plates come together. You can imagine as these plates start to push one together, they could actually push in such a way that instead of one slipping under the other, they both kind of rise up as they cram together. And that creates a process called uplift. And with uplift, you can get rise to very high mountains and ranges of mountains. And again, it's worth noting, all of these processes are occurring because these tectonic plates are banging into one another and pressing against one another as they move on the surface of the Earth. These moving plates create these kinds of phenomena. And another possibility occurs when plates actually slide, not pushing against one another, but sliding side to side. And that can create what's called a fault line. Now, you guys have probably all heard of the San Andreas Fault in California, which is a source of many earthquakes. Here in this region, we actually are situated above the New Madrid Fault line, which is also an active fault line. It's not as active as the San Andreas one, but when it has gone in the past, it has generated some very large earthquakes. So it is something that is a concern to people that live in this region. But regardless, the idea here, as these plates rub against one another, they create lots of pressure and eventually they slip. And it's that slippage that creates the event of the earthquake. And finally, there's one more option. The plates can actually move away from one another rather than into each other, and that creates rifts. Basically, holes form underneath where the plates have separated. Now, when new crust is created in these rift zones, an interesting thing happens. The material that makes up the new crust actually preserves the magnetic field of the Earth when it was created. Think of it like this. If you had a compass and the compass needle was pointing towards the north, and you froze that compass so that the needle could no longer move, that would create a snapshot of how that compass was oriented at that moment in time. Well, it's the same idea. The crust that's created in these rift zones actually preserves the magnetic field of the Earth. The little bits of iron line up with the magnetic field, and so that enables us to tell the direction of the Earth's magnetic field. And what's fascinating about this is that periodically the Earth's magnetic field reverses. In other words, the magnetic field completely collapses and then it reforms such that the North Pole turns into the South Pole and the South Pole turns into the North Pole. So that's kind of a crazy thing, but it happens about every 500,000 years. So, what is it that causes the plates to move around in the first place? It turns out that plate motion is driven by convection. Now, we already talked about convection. It's the motion of mass involved with the transfer of heat. And so, as the heat is transferred, the mass is moving around. And these convection currents in the magma in the mantle region is what's actually driving the motion of these tectonic plates. And so convection is something that's very important. It's important in the process of weather, and it's important in the process of continental drift as well. Now we know that the different continents have moved over very, very long periods of time. So it becomes an interesting question, what would the Earth have looked like a very, very long time ago? And we can actually project backwards how the plates had been moving in the past. And we find that many, many years ago, about 200 million years ago, in fact, that essentially all the continents that we have today were combined into one supercontinent. And that supercontinent is called Pangaea. Pangaea. Now, when we look at all the planets in our solar system, it turns out that not all of them generate magnetic fields, but the Earth does, and the Earth's magnetic field is actually relatively strong. That's due in part because of that liquid core, which is spinning around. Magnetic fields are generally caused by moving charges, and so you have this liquid core that's very, very, very hot, and it's spinning around. And then also we have the fact that the Earth's core is made up of iron and nickel, which are the two elements that are most able to hold on to magnetism. And so these effects magnify each other and create the Earth's magnetic field. Now, it's actually very, very fortunate for us that the Earth has a magnetic field because the sun is generating something called solar wind, which consists of all these charged particles being beamed into space. And the Earth is constantly being struck by these particles that make up the solar wind. But they are largely deflected away from the Earth by our magnetic field. Mars is an example of a planet that does not have a very strong magnetic field. And over time, the Martian atmosphere has actually been eroded by the solar wind. So the atmosphere of Mars is incredibly thin, where the Earth has a very dense, strong atmosphere, and that's something that enables life as we know it to exist here. Now, not all of those charged particles that make up the solar wind are deflected away. Some of them actually get trapped within the region of the Earth's magnetic field itself. And those regions indicated here and here, those are called the Van Allen radiation belts. And there's one there and there's one there as well. The Van Allen radiation belts are the regions where these charged particles have been trapped. That was actually a concern back in the day when we were sending people to the moon and sending people into orbit around the Earth, because the ships carrying the astronauts would pass through these regions with all these charged particles, and it was a concern how to protect the astronauts, or did the astronauts actually need protection. Now, another thing that you can note here is that at the poles, the magnetic field lines are all coming together. They're all joining and getting closer together. And where magnetic field lines come together, that indicates that the magnetic field lines are actually indicating a stronger magnetic field. So the magnetic field's strongest at the polar regions. And what happens as these charged particles spiral around near the poles, they get very high energy, and as they collide with things in the atmosphere, they actually glow. And that creates a process known as an aurora. And if you've ever seen an aurora before, they're really, really pretty. I'm going to put a YouTube of some aurora phenomena in the Canvas module so that you can see them if you've never seen them before, but they can be spectacular. And here you can see a couple of pictures of different aurora like I was talking about, but I'm actually going to put a video up so you can see them really in all of their glory. They're really spectacular. The last topic that we want to look at in this chapter is the concept of the tides. Now let's remember the equation for the gravitational attraction between any two masses. That was Newton's law of gravity, and we had that the force of gravity was equal to that constant big G times the product of the two masses. You multiply the two masses together, and then you divide it by the square of the distance between the two masses. So if we consider the Earth and the Moon as being two masses, we can consider the force of gravity between the Earth and the Moon. Now in grade school you may have learned that the moon is what causes the tides, but we want to be a little bit more specific and see how that actually happens. Now what I need you to understand that what I'm going to describe to you is a little bit of a hand-waving explanation. Fundamentally it's basically correct, but in actuality it's a lot more complicated than this. But this will get you sort of the basic idea of what's going on. And in order to understand that, we have to look at this idea that we're dividing by the square of the distance. And so what that means is that the further away the masses are, the weaker the gravity is. Or conversely, the closer you are, the stronger the gravity is. So what does that mean? That means that the Earth is from here to there. The moon is pulling harder on this side than it's pulling on the center. Because this side is closer to the moon than the center, it gets stronger gravity. And the moon is pulling on the center more strongly than it's pulling on the opposite side. So that creates two tidal bulges. Basically, this side is being pulled up to the moon because it's being pulled harder than the center of the Earth. And then the center of the Earth is being pulled harder than the opposite side, so it's being pulled away from the opposite side, and that creates a bulge over on the opposite side. Now keep in mind, as this is happening, the Earth is spinning on its axis, and the moon is moving around the Earth. And so these motions give rise to basically the oceans being sloshed around as the Earth is being tugged on, and one side is being pulled up, and the other side is being pulled the opposite way. And that creates these two tidal bulges, and it can create high tide and low tide. And as the Earth spins on its axis, the tides will come in or go out. Now, it's worth noting that while the moon is one of the sources of the Earth's tides, the sun actually does have an effect. It's a much smaller effect than the moon because it's so much further away, but it is not negligible. And in fact, it can happen in two different ways. When the sun and the moon line up, as I do in this top slide here, the sun's gravity and the moon's gravity are reinforcing each other, and that makes bigger tides. But when the sun and the moon are perpendicular to each other, or that line rather is perpendicular to that line, you can see that the effects don't reinforce, and that doesn't create as strong a tide as when they are lined up. And the last thing we want to talk about is a very interesting effect. The Earth's tides, rather the moon's action on the Earth's tides, creates a sort of a dragging effect. And that causes the Earth's rotation to slow down. We know that the Earth rotates once around its axis every 24 hours, but in years past, rather than the day being 24 hours, it was shorter, 21 hours, 18 hours, something like that. But because of the action of the moon, over time, the Earth has actually been slowing down. And at the same time, the moon is moving further away out in its orbit. So these sort of effects are kind of interesting. But what will happen eventually is that the Earth and the Moon will enter into a synchronization. So that essentially what will happen is the same side of the Earth will always point towards the Moon. And that gives us the end of this presentation and the end of chapter 7.